My name is Grace Drew, and this is my Physics 2112 Lab 4 circuits. So for the introduction of this lab, the overall purpose was to apply energy and current conservation principles to analyze circuits with resistors in series and in parallel. By predicting the circuit behavior and using multimeters to measure current and potential differences, this lab will also explore the behavior of ohmic resistors and capacitors. Overall, we found that the change in potential difference measured at different points in a circuit aligned with the setup, and that the amount of time needed for just discharging the RC circuits aligned with the value calculated from a theoretical situation. The physical principles we're using for this lab are Ohm's law, which is voltage equals current times resistance, capacitance, which is capacitance equals charge divided by voltage, Kirchhoff's junction rule, which implies that the sum of current going in equals the sum of current going out, and finally Kirchhoff's loop rule, which is the sum of potential difference is zero for a closed loop. So first we set up series circuits. We connected a voltmeter across a 100 ohm resistor, and the reading stayed the same due to high internal resistance. We then replaced a voltmeter with an ammeter in parallel with a 100 ohm resistor. The current readings changed due to a low internal resistance. So here you can see we measured resistance at different points on this graph, and from the points D to E and the points F, G, and H both have flat readings, meaning there's no difference in potential difference. And this is because the wires are ideal and they have zero resistance. In the cases like C to D and E to F, where we see a slope, that means there are changes in potential difference, and this is due to resistance being applied at the points, as you can see here on this diagram. Next, we set up an RC circuit, and the circuit contained a resistor, capacitor, and battery. So when the battery was connected, the bulb lights up but slowly dimmed as the capacitor charged. And then when the battery was disconnected, the bulb lit up and dimmed as the capacitor discharged. So the current is associated with the light behavior. And here you can see when we applied a 10 ohm resistor, it took 9.7 seconds to dim. And then when we applied a 20 ohm resistor, it took 19.2 seconds to dim. And so this shows the overall point that as resistance doubles, so does the time, and these two values are directly proportional. Finally, we have two what-if questions. What if you were doing this lab in real life and used an actual ammeter instead of the ideal simulated one? What's different about a real ammeter, and how would it have affected the circuits I hooked it up to? If I did this lab with real circuit components, how would it behave differently from an actual circuit? So in this case, we know that an actual ammeter has internal resistance, so the internal resistance isn't equal to zero, whereas the simulated one has an internal resistance of zero, meaning that we would see those flat portions with no potential difference, like in the series circuit. There would also be a drop in potential difference and reduced currents in a circuit setup like we saw on the second slide. The last what-if question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. If you're completing the lab with real circuit components, use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery and the ammeter. So in an ideal model, we would have a capacitor being charged instantly, but in real life there's internal resistance, so the charging isn't instant, which is why we see the dimming taking as long as 9.2 to 19.2 seconds.